So a week from today, the IMA will have their statistics workshop related to their special year. So there will be a number of excellent talks starting on Wednesday through Friday of next week. So we will not hold class Wednesday through Friday. I do highly recommend the statistics part as well as the workshop the following week. I will be available via email and online if you do have any questions, but it won't be during the normal class time starting on Wednesday for about a week and a half. But I will create some quizzes related to at least some of the statistics talks and possibly some others. And if you have some favorite talks, let me know. In the meantime, until then, today we're going to talk about a variety of different ways of triangulating data. Then we will talk about multidimensional persistence, and we'll finally introduce the FOM software. I'm trying to get all that covered before we take a break for the IMA workshops. After that, I hope to focus more on applications. If there are particular applications you're interested in, let me know and I'll try to start integrating them into the lectures. But today we will just try to rush through a number of different triangulations of ways of creating data. Fortunately, many of them are related to things that we've seen before. So we created a simplicial complex by first creating a graph by adding edges between points that are close. And then we, in one case, created the Flagg complex. And so we have the clique complex or the Flagg complex where we just got all possible simplices. If the clique existed, we got all the faces, everything in there. So this sort of starting off with a graph and then adding in everything is something standard that we will see for later complexes. Even there's a version in terms of the Delaunay triangulation where you can do something similar if you so choose. Then we've got the check complex where instead we create the nerve. And so in this case, we have a bunch of open sets. And so we will create, maybe about right up here instead, the nerve associated to all of these balls. So that would be if the balls intersect, we fill it in. If the balls don't intersect, we don't fill them in. So that's a standard way of creating a triangulation as well, based upon balls that we'll see in a variety of different circumstances too, where our k simplices are just whenever we've got a non-empty intersection of k plus 1 distinct elements. The nice thing about the nerve of a collection of sets is that if we do have a finite collection of subsets where the non-empty intersections are contractible. So that means basically that if I take a look at an intersection right here, then I can shrink it to a point. So there's no interesting homology. Versus there is one case where it's not contractible. In this case right here, the intersection is not contractible because the intersection consists of two disjoints. So my homology is mostly boring, but not quite. I have two objects, so my H naught is not interesting. I've got two disjoint sets in the intersection. So if I were to create the nerve of this thing here, I have my two sets. Your sets become your vertices, and if the two sets intersect, I have an edge, but that's it. So this is the homology of this thing here is very different from the homology of this object over here. So that object has very different homology. But if all the intersections are nice and contractible, then you do preserve the homology. In fact, you preserve something stronger. You actually preserve the homotopy. We're interested in the homology, so that's good enough. And so thus you would think that we would prefer the nerve, but computationally, the RIPS or the Flagg is frequently easier to work with. So whether we're talking about these starting off with data points and growing epsilon balls, we generally will choose the RIPS instead of the nerve. But even in other cases, we often will choose the flag complex over the nerve simply because of computation is easier. It's easier to put things in. You don't have to store as much data. And if you're growing epsilon balls, then it probably doesn't matter, although, of course, there's many exceptions. So we created another triangulation using Voronoi cells. So remember, we just took a look at all the points. So if my point of interest is V, that red point right there, then I take a look at all the points that are closer. So all the points in this region here, they're closer to this red point than they are to the other 3 points. And we can also get that by taking half planes and intersecting them. So I can take this blue half plane right here, intersect it with an orange half plane, intersect it with a green half plane, and I get this Voronoi cell right here corresponding to this point there. We do that for every single point, and we get our Voronoi diagram. Once we have a Voronoi diagram, we can take the dual of that, or the nerve. So we are seeing the nerve again, where we take, if the intersection is non-empty, so if I intersect one point, I get a vertex. So if I intersect one set, I get a vertex. So each of my CVs correspond to a vertex. If the 2 sets intersect, like they do up here, I get an edge. So we get an edge, we get an edge. And the 3 of them intersect here as well, so we get a triangle too. And I can draw that nicer here. Just note that this straight edge here was the same as the edge that just went above through here. So we just isotope this triangle to look a little bit nicer. But we now have the Delaunay triangulation. It's just the nerve associated to the Voronoi diagram. Let's take a look at the Voronoi diagram. If we throw in a few more points, I now want to compare our Delaunay triangulation to either our Czech complex or our Rips complex. So we've got our Voronoi diagram. We then can take our Delaunay triangulation. In this case, again, I get these edges where, so for each set, I get a vertex. For each 2 things intersecting, I get an edge. For each 3 things intersecting, I get a triangle. And so we can, again, get our Delaunay triangulation after I've simplified it a little bit. And we have this one right here. I want to compare it to my Czech complex, because that's also the nerve, but that used balls, and in particular, we didn't have, this part here did not exist. I would like to relate this to my data, and maybe I don't want to join points that are far away. So how can I stop from joining points that are far away? Well, one of the ways is via an alpha complex. So with the alpha complex, we combine our Delaunay triangulation together with our alpha balls. And so we can now intersect our balls with our Voronoi cells, and now if they intersect, so now if we've got the intersection with respect to the balls, note I did draw my balls a little bit bigger, so now I do have this full triangle here. And so we do have the full triangle. We do have these 3 triangles, and so we do have, and we would also have the full simplicial complex here too in terms of our nerve. And so we can talk about that there as well. And because I'm intersecting these things, actually we don't have the tetrahedron. So that's why I drew this example, so that we don't have the tetrahedron. If I take a look at the intersection, I only have a threesome intersection. So because I'm intersecting it with CV, the most I can have is a triangle, a 2-dimensional complex with the 3 vertices, because I don't have 4 of these intersecting. I might have 4 balls intersecting, but once I look at this complete intersection, I have at most this. And so thus, if I now compare this alpha complex to the Czech complex, in the Czech complex, I got the full tetrahedron because over in this thing here, all four balls intersect. And since all four balls intersect, I get the tetrahedron, which means I get all four triangles plus this ball. Here, it's much nicer. I only get 3 triangles. And these 3 triangles, you know, they're nice. These 4 triangles, they're not quite so nice because they bound a ball. And if you know your data is lying in the plane, and there are higher dimensional versions of this, I could be doing a 3-dimensional complex instead, using 3-dimensional balls instead of 2-dimensional balls. But I would like to stick with the dimension I'm living in. I'd like to stick with, in this case, 2 dimensions. I'd like a 2-dimensional complex out of this. If I'm in 3 dimensions, I'd like a 3-dimensional complex out of it. If I stick to alpha complexes, and in most cases, when you stick to alpha complexes, you'll just have this nice 3-dimensional intersection. Yeah, there is one, you know, place where if I've got 4 points that form a square, then when I do my Voronoi, I will have that these things intersect here. So if you've got that, just add a little bit of noise and get rid of that square. That square rarely happens, so just assume it never happens, and if it does, just get rid of it with a minor perturbation of your data, and then we get to stay with a nice 2-dimensional, you know, cell complex. And so our alpha complex is really what we might be interested in, because then my 2 cells are nice. If I compare this to my full check complex, yeah, remember having 5 points close to each other, I got a 4 simplex. I actually don't care that I have a 4 simplex or a 3 simplex, because when I calculate homology, if I'm calculating H1, for example, I'm only using 2 simplices and 1 simplices. I'm not using 3 and 4 simplices. So that's not really what I care about. But if I take a look at the 2 simplices here, if I take a look at the triangles, well, I've got 5 points. I choose 3 of them to create a triangle. 5 choose 3 is 10. So I've got 10 triangles here, versus if I do the alpha complex, I'll have far fewer triangles. You know, over here, I have 4 triangles, and now I just have 3 triangles. And also my 3 triangles here are much nicer in terms of they don't bound a ball versus my 4 triangles here bound a ball. And so frequently working with alpha shapes is nicer than working with Chex complexes because you do have fewer things. And we can go ahead and do the RIPS version of this if we want to. It actually doesn't change things in this particular example. But the alpha complex is pretty nice. And we can grow those things. So we can grow our alpha complex and create bigger and bigger balls. I also drew this because notice where my balls intersect. These 2 balls, if I take a look at the ball around this data point and the ball around this data point, the smaller balls intersect here and here. The larger balls intersect here. You can notice that this actually gives you an algorithm for calculating your Voronoi diagram. If I take a look at the intersection of the balls, that's actually what creates this, and this will work in higher dimensions as well. So that's one way of creating the Voronoi cells and then using that to create your Delaunay triangulation, and then combining that with your alpha complex, you now have your nice alpha complex. However, computationally, creating this alpha complex, creating your Voronoi cells is more work than just working with the RIPS complex. So in most cases, people still work with the RIPS complex unless there's an actual reason why they want to work with an alpha complex. And if you are modeling something 2-dimensional, you want to stay 2-dimensional, then you frequently want to do this sort of thing. There are also ways to generalize this. We can generalize this by growing our balls at different rates. So with respect to everything, when you're analyzing data, don't feel compelled to be restricted to what already exists or what you currently read about. There's probably something else that already exists that's more general that might be more applicable. So maybe our data point actually might represent stars. And if we want to do interaction between the stars, well, the gravity of one planet might be very different than the gravity of a different planet. And so you might want to have the balls growing at different rates. So you can think about your alpha complex or your balls within your alpha complex as dropping stones in a still lake. And you can drop bigger stones if you want to have a bigger influence, and smaller stones if you want to have a smaller influence. And so all of these things generalized quite a bit other things. Any questions on that? So we can also notice some things. So now we want to do a different type of generalization, and that is to witness complexes. So we'll first notice that we had our set of vertices, and we had that these things spanned a k-simplex. Let's add a k-1 here. So, oh no, it's from 0 to k, so we're fine. So we have k plus 1 vertices spanning a k-simplex. If and only if the cells intersect, so we've got the nerve. That's if and only if there is a point W in Rn whose k plus first nearest neighbors in D are these vertices, and that point is equidistant from them. So let's take a look at what that just said. If I take a look at this intersection point, then this intersection point is closest in terms of to these vertices. So they're closest to these 3 vertices. And more than that, they're also equidistant to those 3 vertices. And that's what this line is. It's the set of all points that are equidistant between this one and this one. This line here are all the points that are equidistant between these 2 vertices right there. And so we will have a k-simplex. Let me start off with the 1 simplex, if and only if there is a point in Rn that is equidistant to both of these, and it's the closest point to both of these. And same thing here, we've got this triangle here because we've got this point that is closest to these 3 points here. So we want to sort of generalize this thing in terms of witness complexes. So instead of restricting the triangles that we created, so one way to get a smaller triangulation was to just say, we're not going to create all these triangles, and that's what we did with our alpha complexes, is we said, we just won't create all these triangles. Well, another type of restriction is to instead say, let's just use fewer vertices. So with the Delaunay triangulation or the alpha complexes, we use the same vertices. We just created fewer triangles. Now what we're going to do is say, let's have fewer vertices. And so we're going to take these witnesses instead that have been basically motivated by the Delaunay triangulation. So let's see how we do that. We basically will choose some landmark sets. At the beginning, we'll just randomly choose them. So I'm going to randomly choose a red set of vertices, and those will be my landmark set, and those will be the ones that I'll use to create my simplicial complex. But these points, the purple points or the blackish points, they did exist in my data, so when it comes to creating simplices, I want to use them to know when to create a simplex. So in the witness complex, we can say that these things will span a k-simplex, but now I'm restricting to only red vertices. If and only if there is a point W in my data set, whose k plus 1 nearest neighbors in L are this thing, and which is equidistant from them. That would be the straightforward generalization from the Delaunay triangulation. That's exactly what we wrote for the Delaunay triangulation. The only difference is that my W was an Rn. Now I'm restricting it to my data point, so that is one difference right here. is that we are restricting this thing to our data set. And then we're now taking a look at, that the k plus 1 nearest neighbors in, now these are the vertices that we are now looking at only. So these are the only things that we will have being vertices in our simplicial complex. That works fine here because, in terms of being equidistant, this vertex is equidistant to these two, so I can get this edge here. But what are the chances that you're going to have a point that's equidistant? It's only when you come up with a fake example like this that things are equidistant. It rarely happens that you have equidistance. And so, in reality, we want to get rid of equidistance. So what we do is we just get rid of, let's go ahead and cancel out this equidistance, get rid of the equidistance part. And just say, we will join it up if the k plus 1 nearest neighbors are this thing, and all the faces belong to the witness complex. We do want a simplicial complex, so if we create a triangle, we better have all the edges and all the vertices. Our vertices will be our witnesses, so these things have to all be in L to begin with. So we will start with our vertices will be in L. We can, say that this thing is, a point in L can be a witness, so this point here is a witness that that point exists. So those are our vertices. Let's take a look at our two-dimensional simplices. Well, if I take a look at the two nearest neighbors of my purple point right here, that would be these two, the two nearest neighbors that are actually in L. If I take a look at the two nearest neighbors that are in L to this point right here, well, it gives me the same edge. And same thing over here, we get the same edge right here. So that edge definitely exists. If we take a look at this, the nearest 2 points to this one is this edge right here. The nearest one is this edge right here. Taking a look at the nearest neighbor of this one doesn't add anything. Taking a look at the nearest neighbors of this, well, that would be these two. That edge already exists. That edge already exists. Notice we don't get a triangle here. So I could look at the three nearest neighbors of this. So I could look at the three nearest neighbors of this one. The three nearest neighbors would be these 3 points. But I don't want to throw in the triangle because the faces don't exist. If the faces don't exist, you can't throw in the triangle. And so we don't throw in the triangle. We just would have our, stuff right here. That would be it. And again, we don't care about these points right here. They weren't in our set of landmark points. We can consider them to be weak witnesses. So this is the sort of weak witness complex. There are other witness complexes that we will also discuss a little bit later. So that is one of the witness complexes. Any questions on that? Let's take a look at another witness complex. If we take a look at this one here, let me go ahead and add a few more edges. This one witnesses to this. This one witnesses to this edge. This vertex witnesses to that edge in terms of the closest points, pair of points. If I take a look at this, this now is so I looked at all the witnesses, all the edges created by the red witnesses. So this is a witness to this edge right here. But now let's take a look at the black ones. If I take a look at all pairs of vertices that are red, that are closest to the black one, well, these are closest. These are closest. And these are closest. And so now I do create the triangle. But now let's take a look at what else I should throw in. Should I throw in this triangle? Well, if I take a look at all 3 things that are closest to this edge right here, what are the 3 things that are closest to this vertex? Well, this one, and that one, those three are closest, but there's no triangle formed from them, and so I don't fill in this triangle. And so the witness complex for this would just be this non-filled in triangle plus these extra edges right here. And so that would be our witness complex. But for computational speed, what are we interested in? For computational speed, we are interested in throwing in everything, and so we might be interested in the lazy witness complex. And so we've got the lazy witness complex. Any questions about that? Okay. Let me go back up to the definition of the weak witness. So we've got our lazy witness is just our flag or clique complex. So we've got our standard witness as well as our RIPS. Actually, it's not RIPS. It is the flag now. It's the same idea where we now throw in all possible higher dimensional simplices, just to save us time in terms of computation. So now this does give us a much smaller complex because we now have fewer data points, and we'll also likely have fewer simplices as a result with our fewer data points. We also want to be able to choose our landmark points. There are currently two main methods of choosing these red points. Random actually works fairly well. So random is actually frequently done. Another common method is max-min, but you also might have some thing particular to your application too. In the max-min, the first point is chosen randomly, but only the first point. Once the first point is chosen, then we choose LK such that this distance here is the largest possible. So do I have an example? I don't have the definition, so let me go ahead and put a few. So we might choose these points here, and then maybe I have lots of other points out here. What we do is we choose the furthest point away. That also means that if your data has any outliers, that outlier might get chosen. It could easily, so this will bias you towards choosing outliers. So you may want to do something about that, or maybe you're fine with having the outliers in your landmark set. But remember, in terms of your landmark set, these are the points that will become our vertices. These are the ones that we are choosing. So let's take a look at this example right here. We randomly choose a point to begin with, so let's go ahead and choose this point right here. If I then take a look at what I think is the furthest point away, I think that might be this point here. So we choose that point. Then we take a look at what we think might be the furthest point. I think it might be this one, could have been that one, but let's assume it's this one. And so, oops, sorry, it should be this one. This is why I colored it in, so I'd be more likely to, if I take, I'm looking at the maximum distance, sorry, the minimum of the maximum distance. So to calculate whether or not there's a point that's further away from these two, I look at the minimum distance, that's this thing right here. And if I want to compare it to the point I accidentally chose, I would want the minimum distance among these two distances. Well, this distance is much further. That's supposed to be a straight line connecting these two, but at any rate, it's much further. This distance here, though, is shorter than this minimum distance of the two from this one here. So thus, I'd want to choose this point and not that point. This point here does look like maybe it's somewhat similar. I didn't actually measure for real, but we'll assume this is the point that's furthest away from my two red points. And so that becomes my third point. And then similarly, we can choose the fourth point that's furthest away from all of them. You can again easily make a mistake and think, oh, this one. but this one is pretty close to this one here. So in terms of minimum distance, I would say this would more likely be the one that's furthest away from all three of them when we take this minimum distance. So any questions about this method for choosing the landmark points? One thing to keep in mind is whether with any of these witness complexes, this may not work for your data. So you're hoping that what you're getting by choosing these landmark points is that you do get a smaller complex. So this will be contained within. So when you do your witness complex, it's going to be contained inside of your RIPS or your check or whatever it is you want to do, however you create it, whether we do the check complex with these or the RIPS complex with these. If I choose fewer points from my data set, then I will have fewer points, and so this will embed with inside of here. But in terms of whether or not you will be getting what you want, will you be actually identifying the circles? Will you see that Klein bottle? It did work for the Klein bottle data. So that's how they found the Klein bottle. They did many, many different, lots and lots of different runs with various different choices. And we're able to find the witness complex for this, but that does not always work. There is another paper where they tried it, and it really didn't seem to work for their data. So there's not a lot of mathematics saying when it will work, but it is something worth trying and seeing if it will work if you have too many data points. If you've got too many data points so that the software just isn't working well on it, then using landmarks is a good method to try. Any questions on that? You will notice that in terms of, so this came from, so this is the first paper that was really talking about these witness complexes, where I could, in order to see this circle right here, I could use all the points, but if I just see these 4 points here, I can still see a circle. It is a rougher circle, but the homology is the same. And so that's the idea behind witness complexes, is you're hoping that if you see this circle, you will still see that if you use fewer vertices. Of course, you'll notice that in this example taken from their paper, this is not the weak witness that I just described. You know, because this point, the closest point to this point is, in L, yes, the closest points in L are these 2 points. There's another weak witness where we look at other things. So, but sometimes you do want to throw in other things, and you want to allow a little bit more than, so there's other types of witness complexes, and so this is actually one of the more common ones, is the strong witness complex. So in the strong witness complex, we again have our data set and our landmark set, and our landmark set is again going to become our set of vertices. But now, in order to determine when we have a K-simplex, we're going to use this, we will join them if there is a witness. So again, we have our witness, just like in the, our Delaunay triangulation, that intersection was a witness. Just like in our weak witness, we had a witness there as well. And in this case, our witness is if we let MV be the distance from our set V to L. So, for example, this one right here, the distance between the red one, it's the minimum of all these distances. It's the minimum distance of all of them. So I don't care about these 3 large distances. I just want to take a look at a minimal distance. And that becomes my MV. And then if I choose an epsilon, I can now grow this MV plus epsilon, and we can go ahead and increase this larger and larger to go ahead and determine when there's a K-simplex. So let's take a look at that, except for, I forgot to reorder these things.
It looks like there's a question.
Oh, question. Was there a question? Oh, without doing the full complex. Oh, so that's a choice. So with the strong witness complex, there are two choices. You can just do, you can just do this without doing the, so you can do this and do the strong complex without doing the flag complex, without throwing everything in. So that is considered the strong complex without me throwing everything in and doing the clique complex or the flag complex, so not too, unlike the RIPS complex. Or you can do the RIPS-like version and just care about, when K is 1, just care about getting the graph first. And so you can instead just do the graph first. So do our graph first. So just get our 1 simplices and then go straight to your flag or your clique complex. And so there actually are 2 different ways of doing this. Thank you, I meant to mention that. With the strong complex, I can either go this direction here, which is the definition of strong complex, or I can do a similar thing to just get the strong graph. I don't think people actually say strong graph, maybe they do. But so I can get the strong graph, and then after that, go ahead and create the flag complex, because that is, again, computationally easier. So you do always have these 2 choices right here. So thank you for pointing that out, because I meant to mention that and I forgot. Any questions about that? Okay, so 2 choices, and that'll be the same thing with however we do this. So questions. Okay, so now that we've got this, I now have, let's go ahead and we'll forget this flag complex to begin with, and we'll create our strong witness complex. If I take a look at, we'll just do an arbitrary epsilon, but now in terms of my witness, let's take a look at this witness right here. Let's assume my epsilon is pretty small. If I take a look at this witness, the distance between here and another landmark point, if my epsilon is small, this won't be a witness to any edges. And so now my red points are less likely to be witnesses, because my M for a landmark point, the distance will be 0. So if my point is actually in my set, well, then the distance between it and itself is 0, and so it's not likely to be an actual witness. Versus if I now take a look at this point right here, my NV might be, well, this distance, and then if I do a plus a small epsilon, well, so that was the distance, but now let's get the edge. The edge now would be this distance right here. So we would have that edge there based upon this distance. So this is not an edge, it's just the distance. Similarly, I can come over here and take a look at MV. MV over here would be the distance between these 2 points for this particular vertex here. For all the red vertices, MV is again 0. But if my epsilon is large enough, then I might say that these 2 points are now close enough, because they might be close enough here. These 2 points would be close enough. Oh, and notice, if this point is close enough to this point, and if this point is close enough to this point, these points will be close enough as well. And so we would actually get our triangle right here. So in our strong witness complex, we'd be getting this type of thing here too. But there's a variety. So that is our strong witness complex for this particular example. Any questions on that? So now in terms of our weak witness, so this is actually, so I should mention in terms of, there are a variety of different complexes. I'm looking at basically two different papers here. One was that 2005 paper from Vin De Silva and Gunnar Carlson. Gunnar Carlson also wrote a paper in 2009. So I already gave you the 2005 reference on a preceding slide. Forgot to include, I think it's Topology and Data. It's a survey paper in the AMS proceedings by Gunnar Carlson, where he basically summarizes some witness complexes. And he also talks about this weak witness complex, where, again, this thing is a K-simplex if and only if the distance between a landmark is less than or equal to x for all I and for all x not in sigma. So in many cases, in terms of your weak witness complex, you're actually talking about the closest point for all x, not just x in your landmark set. So in this case, I want, if I had had a purple point, color, if I had had a dark colored point that's not red, that's closer, then I would not want to do things that are further away. And so that's a common definition of weak witness complex, where it doesn't need to be in your landmark set. It just needs to be, so this is actually, I believe, the more common definition for weak witness, is we're taking a look at that it is the closest point comparing your witness. So in this case, I'm using this as my witness. It's the closest point for all my data points. It's the closest point for all my data points. And this is also discussed in the 2005 paper as well, the De Silva and Gunnar Carlson paper, where we now take a look at the closest points for all of them, not just the landmark sets. So, questions about that? And we can again grow this via epsilon balls. So we can again talk about our epsilon balls. So if I again throw in a point here, if I throw in this point close by, then yeah, this is the closest point, but if I grow via the epsilon balls, I just need to be less than this distance plus my epsilon, and eventually my epsilon ball will be close enough, and so eventually I will get this edge here if I grow my epsilon ball large enough. Okay. Any questions about weak witnesses? So the standard sort of two ones are your strong witness as well as the weak witness. Those are the common definitions, but there are several others available out there as well. But I wanted to have time to spend on complexes, so I was hoping to be able to also cover today a bit of multidimensional persistence. So in our remaining 6 minutes, we're going to go back to our multidimensional persistence. So remember when we talked about the image data, we had 3 variables. One of them is we grew our epsilon balls. And so we could do our standard persistence using our epsilon balls with our K and T fixed. But it would be nice to be able to expand, let our K and T move as well and not fix those. And so we can do multidimensional persistence, where maybe in one dimension you're changing radius, and in the other dimension you're changing another quantity. In this particular case, I stole this figure from this paper right here, or actually this talk. So this is another talk from that 2009 tutorial, where in his example he was talking about curvature. So if we increase the curvature, so here it's not curved very much, we now add in more points as the curvature goes, let more points come in as you increase your curvature. And so we can allow more data points to enter based upon curvature, and then are more balls depending upon our radius. And so in that case, you can do persistence fixing your curvature, and notice all we need is for this to embed within this to embed within that. Or we can do our persistence fixing our epsilon naught, or maybe we will do our persistence doing some other sort of thing. So multidimensional persistence is quite nice. And again, an example, as long as you have a bifiltration, so before we just had a filtration where this embedded within here and this embedded within here, but now we can have a bifiltration where as long as my ij coordinate is less than or equal to here, then I have that this embeds within here. And so we have our bifiltration where the dark vertices exist, the light vertices don't yet exist, the light edges don't exist, the dark edges do exist, and so that's how they're indicating the bifiltration. So in terms of persistence, one thing that we haven't really emphasized enough is this inclusion type of stuff, because that really is in our terms of our persistence. Even in terms of the witness complexes, we would like the inclusions to be nice so that everything gets nicely, that we have our inclusion in terms of our witness complex or our RIPS complex, whatever complex we're using, and that induces a nice linear transformation on our homology groups. And so we can talk about our persistence of vector spaces in terms of our homology groups being vector spaces, and we have these, or our chain complexes being our vector spaces, whichever ones we want to take a look at. And so we've got our persistence in terms of these vector spaces here. And we can do that in terms of any sort of, if we have different vector spaces with respect to epsilon, or different vector spaces with respect to data points, however we want to take a look at it, whether it be with respect to our witness complexes, where we're embedding in our landmark data into our entire data, or whether it be our multidimensional persistence, where we're just varying different operations in terms of our curvature or our density. So however it is, we can still talk about this morphism of persistence of vector spaces and still do this nice algebra where as long as things embed inside, then our analysis is robust. So we actually do have, so these, I took these slides from, these talks given by Gunnar Carlson, where you can actually do epsilon for an arbitrary epsilon, but as before, we restrict to a discrete set, and so we're having time 0, time 1, time 2, and it's the same thing whether we want to do curvature or density. In terms of the others, we often do our own type of, discretizing it to a discrete set. And as we did before, but we never used the terminology, we do have this finite type stuff, where we prefer all our vector spaces to be finite dimensional. You can work with infinite dimensional, but there are more theorems for finite dimensional spaces. And eventually, remember, all my times ended at some point, but I still drew an arrow, and we just said that all our simplicial complexes at some time will just have the identity map for everything else. And it doesn't have to be the identity map, but as long as it's a nice invertible linear transformation so that things become boring after a while. So past n, things become boring. Then we have this finite type stuff. And the sort of algebra that we talked about in terms of the barcodes, we have that classification. The barcodes actually classify it as long as you've got this finite type and as long as we've got this, say, identity afterwards, then our barcodes will uniquely identify this. And we've got that sort of, this is exactly the same thing we talked about in terms of the stuff, but now we want to do this in terms of the two-dimensional things. We can do everything that we did before. We won't focus too much on the algebra, but we can do the same thing we did before in terms of our matrices. It's just now we have two variables. Instead of just a t going this way, maybe I have an x1 going one dimension and x2 going the other dimension. And so we can use this sort of thing to say, when does AB come in terms of my AB? Let's take a look at D. D comes in at time 1. So we'll use our x1, and so it comes in, should that be x1 or x2? I have to look up. I'm assuming this is the x1, but you're basically using these variables. We will quickly do that, but it comes up to the same type of matrices that we did last time in keeping track of when they enter in terms of their two-dimensional coordinates. So if I took a look at AB, it should come in at time 1, 2, except for time 1, 2 is actually 0, 1 in terms of 0, 1 or 1, 0. We'll get these things labeled better next time and talk about our multidimensional persistence. Any questions before we sign off? So finish up multidimensional persistence and start taking a look at more software too on Friday. Or more applications. It might be more applications on Friday and software on Monday. We'll find out before Friday.